Good. So good afternoon or good evening, or good morning, depending where you are. So everyone, so it's a great pleasure to present my lecture in this FHI-aims tutorial series. So today I'm going to talk about a method called the random phase approximation. But in this talk, so random phase approximation, or RP, is a concept which has been well known in physics. So it has been used actually in a lot of different branches of physics. But here, with RP, we are actually referring to a method for first principles electronic structure energy calculations. So I will cover the basics of this approach and also some recent progress. So let's first try to understand what by RP what it really means, right? But here I think by RP it means a methodology in electronic structure theory, and it's really closely related to density functional theory, because it can be, as we will see later, it can be formulated as an approximation to the exchange correlation functional within the DFT theory. So it's normally we say it's beyond the DFT, but it can be understood as an orbital dependent functional theory. It's really beyond the conventional functional, I would say. And it also has a close relationship with the GW method, as Dorothy will talk about later after my talk. So the connection between RP and the GW is because a P quantity for electronic systems, the so-called density function, density response function. So they are both used and computed. So in these two series. So nowadays with RP, we normally use it for ground state energy calculation, and for GW we use it for self energy and the electronic excitation energy calculations. And RP is also connected to the quantum chemistry method, especially the so-called coupled cluster theory. So this coupled cluster theory, singles and doubles, so they can contain different types of diagrams, and RP constitutes a subset, so-called ring diagram. And so it can be understood as a subset of the CCSD theory. So in short, and with RP, and we should know, what we should know is that it captures this non-local electron correlation fact. So this makes RP distinct from other density functional approximations, which normally treat electron correlation energy in a local or semi-local way. So as this figure shows, it also bridges DFT, GW, and the quantum chemistry methods. So this is a brief introduction. So now, this is the outline of my lecture. So in the first part, I will introduce the basic concept of RP, and also discuss a little bit about its early history. So as an approach to compute the correlation energy of interacting electrons. So in the second part, I will talk about how RP is implemented in a first principle code, and especially how it's implemented in FHI-aims. Then I will also present some examples of its application in chemistry and material science. to give you an idea and in what situations this method might be useful. And nowadays, RP is not a single method. Normally, we use it refer to a class of methods which are based on RP. In fact, one can also go beyond RP by adding additional corrections so that to achieve better accuracy. So I will also briefly touch this part, but not much. Mostly covering the work we have done in the past and in this field. And finally, I will talk about some recent progress in the RP community, including both our own work and work by other colleagues in the field. So in the first place, why do we want to do? Why do we need such an approach at all? So we know DFT is a conventional approximation. For example, local density approximation and generalized gradient approximation, and they are very successful in materials calculations, and because they offer a very good compromise between the computational cost and the accuracy. So that's maybe in the first principle calculation, maybe a large part, a major part of this calculation are done and based on these approximations. But these approximations, as you may know, and they do have certain limitations. Okay, we can list some of them. For example, when you have a system which has mixed bounding characters, that means that you have a combination, for example, between metallic bond and a van der Waals bond. And in these cases, using GGA may not be good enough to have the correct energetics. Here we have several different situations. For example, when you have mixed physical adsorption or chemical adsorption of molecules on metal surfaces, or some organic inorganic interfaces, and or energy difference between different polymorphs. To capture this delicate energy difference, you often need to go beyond LD or GG. So there are some other situations. For example, when you have a situation where both ground state energy and the energy gaps are important, because we know sometimes these DFT approximations, they are good for ground state energy, but they are not good for energy gaps. There are more challenging situations. For example, when the system has near degeneracy, when you have bond breaking, transition state, or transition metal oxides, and so this situation, we also need approaches beyond the LDGG. And in fact, in the past 20, 30 years, there are a lot of electronic structural methods which goes beyond LDGG, either because to improve the accuracy for ground state energy calculation, or by improving the energy spectrum. So in fact, there I just list some famous methods which are either developed from quantum chemistry community or within the DFT method by going to better functionals, or from some solid state communities by correcting DFT in one way or another. And the RP-GW, this kind of approach, they are based on the response function of the system. They are actually just two of these very many approaches. So since we have so many different approaches, which are maybe best suited for different problems, but we can, if we want to group these different methods, maybe we can, and I think it's a good idea to think about this method and in terms of this hierarchy here. And in this hierarchy, we can roughly classify these electronic structure methods into three major categories. So in the first category, these methods, they only need the input of densities or its gradients, including the gradient of density or kinetic energy density. And for example, the first three rounds of the DFT theory, including LD-GG or matter-GG, they belong to this round. And these are computationally very efficient, but they have some limitations. It's hard to overcome within this framework. And if we want to go further, one need to incorporate in the theory the density matrix, or equivalently the occupied orbitals. So these include the well-known hybrid functional or hybrid matter-GG or density matrix functional theory. And they need orbital information, but only occupied orbitals. But if you want to go even further, for example, if you want to describe van der Waals interactions in a seamless way, one need additional information including the unoccupied states, as well as the eigenvalues. So this type of approach including RP, GW, MP2, or double hybrid functions, or all these quantum chemistry methods. So they will need all these spectrum, both occupied and unoccupied states, and the eigenvalues. So these information are equivalent to the single particle Green function. And so, by the way, and if you have any questions, actually you are welcome to interrupt me, and so we can discuss the questions. Or you tell the chair of the session. And now let me briefly discuss about the history of RP. And the concept of this approach appears in early 50s. And so at that time, the scientists are concerned about the coordination energy of homogeneous electron gas. And this is a very important question in solid state physics theory. When they try to compute this quantity, initially by order perturbation theory, they find starting from the second order, the coordination energy diverges. So this approach does not work. And has been, so this problem has plagued the community for quite some years, quite some time. So only in early 50s, and Baum and Pines realized for these electronic systems, it's a good way. A good approach is to separate the so-called collective modes and the internal modes or individual modes of the particles. And they do so by invoking the so-called RP approach. So I will talk about this a bit later. But here the importance by doing so, they can now treat the electronic homogeneous electron gas and can compute quite accurately the energy of these model systems, which actually open the way to treat the metallic system in general. And shortly after that, Linhart has developed a self-contained field approach to homogeneous electron gas. He defined a dielectric function for the system. and introduce the function which is called the Linhart function, and for the system. So this Linhart function is nothing but the non-interacting response function for this model system. For real systems, we normally call it a non-interacting response function or the Cauchy response function, which is a key quantity in both RP and GW calculations. And in 1957, Bruckner and Gell-Mann realized the RP introduced by Baum and Pines is equivalent to the so-called sum of ring diagrams to infinite order. And after that, now, so this approach now has a diagrammatic representation, which actually is a quite convenient way to understand and to formulate this approach. And in the same year, Harvard introduced this concept of Xinguo Ren action. And so this Xinguo Ren action actually is a quick quantity for many neutron systems. And many following development are based on this quantity. And in 1965, he introduced this GW approximation, and whereby the self-energy is given by a product of the current function and the Xinguo Ren action. So Dorothea will talk about this in her talk. So what's the concept of Baum and Pines for RP? Actually, this paragraph was copied from their paper in 1950. So here is this name random approximation first appeared. So the essential idea behind this approximation is this. So when you apply an external electric field to an electronic gas, so there are two kinds of response of electrons to the external field, external oscillating field, let's say. So one of the response is in phase with the wave or the external field, so that the phase difference between the particle response and the wave producing it is independent of the position of the particle. So this response contributes to the organized behavior of the system. The second type of response has a difference, phase difference, which depends on the position of the particle. And because the location particles are general, there is a general random location of the particles. This second response, they tend to average out to zero when there are a large number of electrons, or when there is a high electron density. So they average to zero, and as a first approximation, you can neglect the contribution arising from this. And this procedure, they call the random phase approximation. So this is the concept, a theoretical consideration. So mathematically, it can be understood in the following way. One can define a density fluctuation operator. This rho Q is a Fourier transform of the density. So, and then, of course, when the density changes over time, and this the Q component of density also changes over time. If you write down the equation motion of rho Q, you'll find that there are terms which only depends on the Q component of the density fluctuation, and there are terms from other momentum. The coupling of the Q component with other momentum appears in a phase factor here. And because this xi, the location of the particles, they are quite random, there are quite many of them. So this exponential phase factor, the average out to zero. So and this second line is neglected from the equation motion of this rho Q. And from this one can derive the random phase approximation. And then the derivative function energy itself will be derived from this approximation. So this is the basic concept. But how is this related to the first principles total energy calculation? And to understand this, one has to introduce another concept called adiabatic connection structure. So this adiabatic connection is a mathematical tool to construct the exact exchange correlation energy within DFT. So the idea is the following. And suppose we have a physical system of interacting many electrons, where it's described by this Hamiltonian, which contains three terms: the kinetic energy, the electron interaction energy, and the external energy. Within cosine theory, so we have a model system which only contains the kinetic energy operator and the external and the auxiliary field. So this non-interacting cosine system is required to have the same density as a physical system. So this is the definition of a cosine system. So the physical system and the cosine system define two limits. So only connection that they have the same density. And we can define a series of fictitious systems with skewed interparticle interactions. So this skewed interparticle interaction, and so where we skew the Hamiltonian with the parameter lambda in front of the electron-electron interaction. And when lambda equals 1, and we have the physical system, and when lambda equals 0, we have the cosine system. So we choose the external potential such that electron density is kept fixed along this path. So if you have this setup, and one can show that this exact exchange correlation energy within DFT, within cosine DFT, is given by an integration over this coupling parameter lambda from 0 to 1. The integrand, which depends on lambda, is called the exchange correlation potential energy, which is given by the interaction energy subtraction the Hartree energy. So this UX is the exchange correlation part of the interaction energy of the lambda systems. So this procedure can be understood or can be illustrated by this integration over this lambda. So the exchange correlation energy is given by this area, heated area above this curve here. And of course, by doing so, one had to have the exact exchange correlation energy, one have to do this integrand, which we still don't know. But the trick here is that one can approximate this integrand by finding suitable approximations. So by finding this approximation, one has to evoke another thing called the fluctuation dissipation theorem. So within the fluctuation dissipation theorem, and this integrand, this exchange correlation potential energy, is connected to the density response function, this k lambda, which is also dependent on lambda. This lambda, k lambda, describes how the density changes with respect to an external field. So both depending on the time. So and this is a Fourier transform to the frequency domain. And by doing so, the exchange correlation energy now is connected to the density response function. So now one can imagine, one can make an approximation for this density response function, and this approximation will translate to an approximation of the exchange correlation energy. So how to make an approximation to this response function? And in fact, this response function satisfies a Dyson equation. This Dyson equation links to this K0. It's a response function of the Cauchy system. Yeah, it's also with lambda equals 0. So it links to this K0 and this K lambda. This kernel has two parts. The first part is V, is this a Bayer-Coulomb interaction. The second part is called FHI. This is the exchange correlation kernel of defined within TDDFT. It's the second derivative of the energy with respect to density. As the first approximation, one neglects this F contribution from X by setting it to 0. And by doing so, one will have this RT approximation for this response function. And now you plug this approximation back to the ACFD expression for the energy, and one will end up with a closed expression for the correlation energy of RT. And finally, you will find that RT can be written in terms of just the Cauchy orbitals and orbital energies. And in this way, RT is defined as a functional within DFT, but it's an orbital and orbital energy dependent function. They only explicitly depending on the density, but explicitly depending on the orbitals. And this formulation was originally done already in the 70s. But at that time, it was not computable because it's computationally quite challenging. Only in early 2000, people were able to apply this formulation to real molecules. And shortly after that, several code has implemented for RT, both for molecule geometry and for solids. And quickly, RT has been applied to a variety of different systems. And about 10 years ago, we wrote a review article about the theory and applications of RT in chemistry and material science. And actually, in 2016, David Pines, so the original, so he invented the concept, right, proposed this RT. But at that time, just shortly before, and he passed away, he wrote a review article for the RT. The title is Emergent Behavior in Strongly Correlated Electron Systems. So in this review paper, he actually mentioned that 60 plus years later, after RT was first proposed, so this concept continue to play a significant role in different branches of physics, and especially in computational chemistry and material science. And I also refer to the review paper we have written. This paper describes the impact of RT in theoretical chemistry and material science, and also gives some details, a very nice summary of our paper. Okay, so far about the history. Now, why is RT interesting for material science? I think people got interested in this approach because it has several nice features. So the first feature is that it automatically and seamlessly including the van der Waals interactions, especially this non-trivial part of van der Waals interaction, including their non-additive anisotropy and many-body screening effect of the van der Waals interactions are properly accounted for. The second feature is that when we do RP calculation, we always treat the exchange energy exactly. And by doing so, the self-interaction in the heart rate energy is cancelled out. And this will clear many self-interaction problems in conventional DFT approximations. And the third feature we can say is that an RP seems to be able to describe different bonding types and equal footing, including ionic, covalent, metallic, and van der Waals bondings. So this will make it useful when you have a very complex situation which has different sorts of different types of bonding characters. Another distinct feature of RP is that it seems to describe the so-called static correlation very well. For example, it gives the correct dissociation limit of H2. And because of this feature, it can give a quite good chemical reaction barrier heads, which are often underestimated by the conventional density functional approximations. Okay, these are the next features. And so how do we do RP calculations in practice? In most practical calculations, RP is carried out as a single point post-SCF approach. So it's based on references from a preceding semi-local or hybrid functional calculations. So you first do a normal DFT calculations. You have the eigenvalue and the eigenfunctions. And then the RP total energy contains two parts. The first part is just the Hartree-Fock energy, but the Hartree-Fock energy evaluated with the Coulomb orbitals, or in case of Krabbe functions, the generalized Coulomb orbitals. The second part is RP correlation energy, which depends on both the orbitals and orbital energies. So we will show how this is evaluated. And in this procedure, so of course, the RP results will slightly depend on the starting point. So that's why often we denote RP at this functional, this symbol after this at means the reference when used for RP calculations. So typical choices are GGE and hybrid functionals, but this definition is not that significant. So there are some quantitative dependence, but qualitatively often they give consistent results. So as I mentioned, so one next feature of RP is that it can describe the van der Waals interactions. Why is that so? This is because this van der Waals interaction is given by the non-local coupling between spontaneous quantum charge fluctuations separated in space. And for example, you have two charge neutral system. They have no permanent multiples, but the density fluctuates over time because of a quantum nature. And these fluctuations are coupled by long-range Coulomb interactions. So the way to understand why RP can capture these type of interactions is from their diagrams. So RP is a summation of this so-called ring diagram to infinity. Actually, at second order, which is given by this diagram, one can already describe the van der Waals connection. So here, these two bubbles, each bubble describes the fluctuation of one molecular systems, and they are coupled by these long equivalent actions. Although second order perturbation theory already described the van der Waals interactions, but they often overestimate this interaction because this density fluctuation is given by the bare at the bare level. By summing up this ring diagram to infinite order, one essentially normalize this density response from the non-interacting one to a RP interacting RP response function. And finally, one can show that this interaction energy between two charge neutral systems given by also C6 or R6 at a large distance. And this coefficient is given by this integration over the RP probability of the monomers. And this property is called dispersion consistent. Okay, and this is the first part. Now the second part, let's see how do we implement this approach. As I mentioned, to do RP calculation, so one first solve a Cauchy equation to get these eigenvalues and eigenvectors. And from these eigenvalues and eigenfunctions, we can explicitly construct this independent particle response function. Now, this equation is known. And in real space, but to represent this in a computer program, we need to discretize this response function. So in this case, we typically introduce a basis set. We call it the auxiliary basis set, the P here. So within such a basis set, this non-direct response function becomes a matrix. So at each frequency point, it becomes a matrix. So so this response form, this matrix form of this non-direct response function is a key quantity, and one need to compute. Once you have that, and then one also need to compute this bare pulling action within the same basis set P. So once you have these two matrix form, and the RP correlation energy can be computed by simple matrix algebras. So so the key quantity is choose a set of auxiliary basis function to expand this K0. And really depending on what basis set you use in your DFT calculations, so this auxiliary basis can be chosen in different ways. Typically in plane wave community, one also use the plane waves for these P's. So in our case, we have the atomic orbitals. So we also need to introduce another set of atom-centered basis set to represent this response function. But the optimal auxiliary basis set, they are different from the orbital basis set. One needs to expand the Cauchy orbitals. So here, the key point is that with the atomic orbital basis set, we have two sets of basis functions. So one set is the basis function to expand the Cauchy orbitals. So another set is this auxiliary basis function to expand the response function. So this is the key point. And then in FHI-aims, we have designed an automatic procedure to construct this kind of basis set, auxiliary basis set on the fly automatically. Okay, and now once this P function is constructed, and we need to compute this expansion coefficient, we need to expand the product of two Coulomb orbitals in terms of this auxiliary basis. This expansion coefficient we call it C here. So this is the P quantity. So once we have this C coefficient, we can plug this into this expression here to compute this matrix form of the non-interacting Coulomb response function. So once you have this guy here, the rest is quite straightforward. And what I have shown here is for the molecule systems, but for periodic systems, the additional complexity is that the Coulomb orbitals has a Q dependence. So now to this expansion coefficient, now they have dependence on two different block of vectors, because they are expansion of two Coulomb orbitals at two different key points in terms of auxiliary basis. Auxiliary basis has a Q vector which depends on difference of the two block orbitals. But anyhow, once you have such an expansion coefficient, you can still plug into this expression here. Now our response function also depends on a Q vector here, and to compute this response function at each Q point, one needs to sum over the Boolean zones. And this step, the computation cost for this step is given as the fourth power of the number of basis functions or number of Coulomb orbitals, and the second power of the number of key points in the Boolean zone. So this is the conventional implementation, which has this scheme. So you can see that it's quite expensive. So once this is done, one also need to compute the Coulomb interaction within the same basis set. And once they have two pieces, you can still plug in this into the RP correlation energy expression to compute the RP correlation energy. The only thing one need to pay attention to is that the gamma point, where once Q is to 0, and there are special tricks and to have a good convergence. So all these things I have discussed have been implemented in FHI-aims, which you already know quite a while. And this is, yeah, and actually in addition to the implementation in FHI-aims, RP has also been implemented in several other codes, either for periodic systems or for molecules. And at the moment, the implementation in FHI-aims works both for molecules and for solids. I think in the exercise in the tutorial tomorrow, you will have a chance to run the code for some periodic systems. Okay, and let's see how RP performs for real systems. So here is a test set for van der Waals interactions, including 3 types of systems, including water damer, and these are the hydrogen bonding systems, or some mixed bonding systems, or some pure van der Waals systems. So here we see for hydrogen systems, for hydrogen bonding systems, normal GGE and hybrid function also described quite a while. But for dispersion and mixed bonding systems, RP really is a significant improvement over its conventional functional, because by definition, by constructing these functional, don't capture its pure dispersion interactions. So this is another application of RP to the absorption systems called the Xinguo absorption puzzle. The puzzle is the follows. When you put an Xinguo molecule on top of this copper surface, copper 1 surface, one may ask the question, which absorption site that Xinguo prefers, because at different sites there are hollow set, 3-foot coordinate, hollow set, there are top set, there are bridge set, etc. If you do a conventional LD or GE calculation, it gives you the result that this hollow set is preferred. But the experiments tell that this hollow top set actually is the most stable absorption set for CO. And we did the calculation by climbing this Jacobi ladder from LD to PV to hybrid functional and finally to RP. One can see that at the level of RP, indeed, this absorption, the order of the absorption energy is reversed, and the top set is indeed the most stable absorption set. This is another example about the phase transition of this rare earth metal theorem. And for this example, for this system, there's a very famous structural transition of a so-called gamma phase and alpha phase. So both of the two phases has FCC structure, but they have a big volume collapse. So how to describe this transition is quite challenging to density functional theory. And we find that for this system, actually, if you do a hybrid functional calculation using PV, one has two stable solutions. So these two stable solutions are consistent with the two phases of the alpha and the gamma phases of this material. But the energy ordering given by PV0 for these two phases are not consistent with the experiment. So only after a correction by adding RP correlation energy, and one can see that this alpha phase is preferred and over the gamma phase at ambient conditions. So this example shows that RP correlation energy is really crucial to correctly characterize the different polymorphs of crystals. Actually, similar calculations have been done for several other materials, and in quite several materials, similarity is the only approach currently which can correctly describe such energy differences. So again, so this is the third example about this the phase structure of the rare gas crystals. So the interesting question is that these rare gas atoms, when they crystallize, when you lower the temperature, they prefer to crystallize in the FCC structure, but not in the HCP structure. The question is why. A lot of calculations, theoretical calculations, cannot correctly describe this phenomena, kind of give the red energy difference. And recently we performed a calculation with the RT plus some corrections. We call it renormalized synchronous corrections. And with this approach and with very converged calculations, we can show that at a volume range, that means when so RP indeed gives the lower energy for the FCC phase. So, but this energy is really, really small. So one has to do very highly accurate calculation to see this correct description. Based on that, one can compute a phase diagram of this system. So actually, I see that I'm running out of time, right?
Xinguo, yeah, I just wanted to say we are 4 minutes actually over time.
In fact, I can stop here or go to the end to check if there are questions.
Sure, no problem. So thanks, Xinguo, for the fantastic talk. And here, I think we have time to take few questions. Is there any questions that somebody wants to ask? Okay, if there are no questions, I have a question, Xinguo. I was wondering, in terms of the computational cost of the RPA method, how is it compared to the computational cost of other DFT functionals, for example, LDA, GGA, and etc.?
Yeah, that's a good question. So as I have shown that this canonical scaling of RP and skews as the force power of the size of the system with a pretty large prefactor. So the form of scaling is the same as a hybrid functional, but it has a larger prefactor because there is a frequency dependence, which give you one big prefactor, and one also typically need larger distance set. So typically, really depending on systems. So the computational cost can be, let's say, 1 to 3 order magnitude compared to, let's say, GGA. So it's typically 1 order magnitude more expensive than hybrid function, let's say. But currently, people are working on lower scaling and RP implementation. So there are already several implementations available. With this lower scaling, seems that which allows you to rather large systems. I mean, with modern computers, nowadays one can still treat a few hundred atoms. So seems not much difficulty.
Okay, thank you. Any other? Sure.
Okay. Xinguo, one question on say the starting point dependence of RPA. I mean, you said that one should not use the Hartree-Fock orbitals, but generalized Cohen-Sham orbitals. Now, still, we are not doing RPA in a self-consistent manner, right? So my question would be actually, what knowledge do we have so far on the starting point dependence? I mean, we know that GW, for example, has a quite significant starting point dependence. So how is there experience with RPA already?
Yeah, good question. So with RP, so first of all, if you start with the Hartree-Fock, it's quite bad. So this is well known. And with Cohen-Sham orbitals, typically, one can describe the long range part, the van der Waals connection pretty well if you use Cohen-Sham orbitals. So actually, that's actually the motivates. One use Cohen-Sham orbitals, which has smaller gap, to describe the response property of systems. But for systems which has let's say quite a strong correlations, where let's say GGA is not good starting point to quantitatively describe systems, one may prefer hybrid functions. Let's say, and when we do this Theorem method or other correlated materials, seems with GGA is not a very good starting point. So I would prefer to use either Cohen-Sham or hybrid functional, let's say, with a small mixing parameter. So these are typically good starting point for RP. So this is the experience so far. But eventually, I hope will be to go to self-consistency in some manner. And I think this is still study in progress. I think so far there are no consensus yet. Which self-consistency approach is good for RP?
Okay, I have another question, but actually there was just one question related to that in the chat. Maybe you can first answer that one.
Yes, so Siri Mata is asking, is RPA calculation essential to do GW and the BSE in sequence?
No, it's not essential. Actually, GW calculation, and so RP and GW calculation, they have some common part. And that's the response function I have talked about is K0, right? Linear random response function is a common piece for both RP and GW. So once you have K0, so if you do RP, you can directly go to RP correlation energy, which you only need a K0. And you can go to another route to compute the synchronous Coulomb action and then GW self energy. So that's another route. But RP is not the prerequisite for GW calculations. Only that they have some common piece. You don't have to do RP, let's say, in order to do GW or BSD.
Thanks, Xinguo. Matthias, would you like to ask your next question?
Yeah. So that relates to this relation between RPA and coupled cluster theory.
Yeah.
In principle, say all Hartree-Fock-based methods have problems with metallic systems.
Yeah.
And that's why also the RPA is good for metals, and it's actually good for metals also because we start with density functional theory.
Exactly.
Now, so we are working at the moment, and we means actually Evgeny Murman, who is actually in the tutors, working on the coupled cluster theory for aims. My question really to you is this relationship, because I wasn't sure if I understood that, to be honest. You said actually there's a relationship in the diagrams between RPA and coupled cluster theory.
Yeah.
Can you explain that again a little bit in more detail?
Yeah. Yeah. So the coupled cluster, so there are different ways to understand this relationship. So I prefer to understand this relationship from the diagrams. And so let's say if you do a CCD, the coupled cluster double theory, right? One can write down the Goldstone diagrams for this theory. So you will find that in CCD you have the ring diagram, and you have ladder diagrams, and you have some mixed diagrams of rings and ladders, and some additional ones. So these are the diagrams in CCD. But if you throw out all other diagrams, keeping only the ring diagrams, so you will end up with the RP. So from that perspective, so RP is kind of a subset of diagrams in CCD. So actually, from this perspective, one would say that CCD must be better than RP. So, but in fact, this is not necessarily so, right? In certain cases, it's so, but it's not always so. Because CCD typically CCSD is pretty good, but CCD itself normally one needs to add singles to get to have a very good theory. But actually, as you know, we also found that these singles are also quite important for RP, right? RP also need to include the singles for some, in many cases, right? To have a very good cohesive energy, binding energy, etc.
I mean, if you have a system with a band gap, then I would say in coupled cluster theory, it looks to me really like a systematic convergence you can do with double triples and maybe even higher orders.
Yeah, yeah.
So a system with a band gap, I would say, I would trust the coupled cluster more. No, a system with metals, with metallic behavior, we have no experience at all with coupled cluster theory if and why it should work, right?
Yeah, actually, also not many experience, not much experience with RP. I think RP for metals, we have some results, right? But not a really systematic study. I think it's still not there, I would say.
Okay, thank you.
Yeah.
Thanks, Xinguo. I think we have time for maybe one or two more short questions. Well, I have a question, Xinguo. I think you said that for this RPA-based method, we only need the information about the occupied Kohn-Sham orbitals, right?
No, both occupied and unoccupied, and also the orbital energies. So essentially, you will what you need is this non-interacting current function. So yeah.
And right now is performed as a post-SCF calculation, but ultimately would it be better to be used within the self-consistent procedure? Is that right?
Yeah, if and people are working on this. How the first thing is what is self-consistency? Right? We need to define a self-consistent scheme. The turnout once the functional depends on the eigenvalues like in RP, and the self-consistency issue is quite tricky. So there's not a unique way to define a self-consistent scheme. So one early scheme people have worked on is so-called OEP, optimized effective potential approach. It means to find an optimal local potential which minimizes the RP energy. But this approach, first numerically quite unstable, and secondly, it also does not really help students, if I understand the situation correctly. And now people tend to have a really generalized quotient scheme, which corresponds to RP energy. I think Wei-Tao Yang and Philip Forscher, they have some work along that directions. But but this community have not really agreed on really one self-consistent approach that is the best, or there are a lot of benchmarks. So far, this has not been done yet.
All right.
I think that's theoretically not really settled question. Yeah.
Okay, thank you. And there is one question in the chat. I think this probably will be the last question. I read it out loud. When we assess van der Waals functionals for the binding energy of layered materials, we use RPA as reference values. Being an approximation, how far can we trust RPA as reference values?
Yeah, that's a very good question. Compared with other more same empirical approaches, I would trust the RPA more for layered materials. But certainly, I would say this is RPA certainly not the ultimate answer, because RPA, although it can describe van der Waals action very well qualitatively, but the C6 coefficient coming from RPA show a little bit underestimation. And this means that for layered materials, most likely RP will underbalance a little bit. Yeah, not much, but a little bit. So without other reference, let's say, and I would trust RP more. But if you can do a CCSD parenthesis T calculation, perhaps that would be better, although computation will be very demanding.
Okay, thanks, Xinguo, for the answer. I guess with this question, we can end the first talk here and take a short break, maybe around 10 minutes break. And then after we can listen to Dorothea's talk. I just stopped the